And here I am. And I'll just do it in the OneNote. So I just need a new page. Here we go. Fantastic. I'm sorry about all the delays. Right, let's get started properly. So what I'm going to try and do now is have another look at how to get the derivative of sine and cosine functions from first principles. And then I'll do some of your problems, and then we'll do some more theory, and then I'll do some more of your problems and so forth. So let's imagine we want to differentiate sine theta. So if we think about the definition of sine theta, if I've got a right angle triangle of with an angle here of theta, then sine theta is the opposite here. Now, if we think about differentiating, we need to think about what happens if this angle changes a little bit. So instead of putting the angle theta here, I'm going to make this the angle theta plus delta theta, where delta theta is some change in angle, which is assumed to be small. Okay, so that's this height here of this triangle is sine theta plus delta theta. Now, what we really want is we really want to look at the difference between sine theta and delta theta and sine theta. Now, if I draw another length, line of length 1, and this time make the angle of sort of projection, or the angle of elevation theta, rather than theta plus delta theta, then it becomes sort of clear that the length that I want to find is this length here, which is sine theta plus delta theta minus sine theta. And so the question is, how do I find that yellow distance? And the triangle that I'm going to consider in order to do this is I'm going to think about this triangle I'm going to think about this right angle triangle here. And in order to think about this right angle triangle, I'm going to do a little bit of angle chasing, considering this bigger triangle here, which has got length 1 and 1, which is an isosceles triangle. Okay. And to remind myself, if I draw an isosceles triangle like this, with length 1 and 1, then I would find I can consider the big right angle triangle that encompasses everything. So this big right angle triangle. Okay. And if I do a little bit of angle chasing here, I get that this angle is 90. This angle is 90 minus A. this angle in here is therefore, I've got 90 minus a, so I've got 180. And so to make up a full angle of 360, I've got 180 plus a minus b. And then if I use the fact that these two angles are the same, so this angle here and this angle here are the same, then this red angle in here must be b minus a over 2. Okay. Because this angle, the angle here is 180 plus a minus b. The other two angles are the same, so I've made them add up to 100. I've made them add up to 180. The next angle that I can find is this whole angle here, which is a plus b minus a over 2, which is then a plus b over 2. Okay, where's this geometry taking me? Well, I want to understand the big green right angle triangle. So my isosceles triangle, which is 1, 1, and then b minus a over 2, I can split it into a right angle, and I can get that this length here is cos b minus a over 2. And then to get the complete length, I multiply that by 2. So this long diagonal is cos b minus a over 2. And then the opposite side is then the sine of the angle a plus b over 2 times cos b minus a over 2. So I get 2 cos b minus a over 2 sine a plus b over 2. But this vertical height is the same as this vertical height, which is sine a, plus this vertical height, which is sine b. So what I've proved here is a result which some of you might be familiar with, which is sine a plus b, sorry, sine a plus sine b is equal to 2 cos b minus a over 2 times sine a plus b over 2. Okay, and this is an identity that is true for all angles. Okay, I could have done similar geometry on the diagram on the left, this one, but the angle chasing and the sort of finding the angles is a little bit more tricky. But what I can do instead is use this identity that I've just derived to get an identity for sine theta plus delta theta minus sine theta, because that is the same as sine theta plus delta theta plus sine minus negative theta. And then I can use my identity in the red box. And the identity in the red box would give me that this is 2 cos so this turns into sine cos of the difference. So that's theta plus delta theta minus theta. So that's theta plus delta theta over 2. And then we've got sine of delta theta over 2. And so now we need to think about what happens when delta theta goes to 0. Okay, because that's the essence of differentiation. Now the first term, it's very simple to understand what happens when we go to 0. We know that cos theta plus delta theta over 2 is just going to go to cos of theta, because cos is a nice continuous function. So what we need to do, therefore, is understand this sine delta theta over 2. So we need to understand, we need to get a good approximation for a value of sine when theta is small. So let's think about a small angle. Let's think about delta theta. And let's imagine I draw a right angle triangle with height sine theta. Right, I'm going to check if people are, if my computer is actually working and all the technical gremlins are over, and also check if people are alert and awake. Can you give me an expression for the length AB, where AB is the arc? Can you give me an expression for the length AB, where that's the chord? So that's the chord AB. And then can you give me a length, an expression for this vertical height, AC? Right. So the chord AB, because I've got an isosceles triangle, I could split the triangle in half. This is now 90. This angle is delta theta over 2. 1 is the hypotenuse, and the distance to the midpoint is sine delta theta over 2. So the chord AB is 2 sine delta theta over 2, because it's twice the distance to the midpoint. The distance AC, the height, is tangent of theta. And the arc length AB, well, the fraction of the circle that I have is delta theta over 2 pi. The total circumference of the circle is 2 pi. The 2 pi's cancel, so the arc AB is delta theta. Now, would anyone like to just make an intuitive suggestion for what happens to this arc length AB, sorry, this chord length AB and this arc length AB when delta theta is small? So when delta theta is small, the circular arc is essentially a straight line. So you'd expect the distance along the straight line and the distance along the arc to be very close to one another. So what I can say is that 2 sine delta theta over 2, to a very good approximation, is delta theta. But that is now really helpful in this exact expression that I've got for sine theta plus delta theta minus sine theta. Because I've got this exact expression, sine theta plus delta theta minus sine theta is cos theta plus delta theta times 2 sine delta theta over 2. But what I've just said is 2 sine delta theta over 2, to a very good approximation, is delta theta. And also, to a very good approximation, when delta theta is small, this cosine term, the delta theta over 2, just disappears. So I can say, to a very good approximation, this is just cos theta delta theta. Okay. Now, why are we essentially done? Okay, because this is exactly what we want. Because we can now write sine theta plus delta theta minus sine theta over delta theta to a very good approximation is cos theta. Okay, so what does this tell me about sine theta plus, what does this tell me about the function sine theta? Okay, well, this is exactly the fraction that you get in a rate of change, because the numerator is just the change in sine theta, the denominator is the change in theta. So what I've established here is that the derivative of sine theta is just cos theta. Okay, any questions at this point? Or if you're happy, put a thumbs up. Okay, but I've also got a question for you, is you shouldn't act, the thumbs up in some sense is the wrong answer. Okay, my question to you is, are there any problems? Are there any sort of bits of this proof where there's, where you're unconvinced? So, if you're happy and you understand it, put a thumbs up. But even better in this instance would be to spot kind of potential flaws in the argument. Okay, great. So someone said, if theta is large, could it ruin the approximation? Well, yes. Yeah. So if theta is large, cos theta plus delta theta over 2 is no longer approximately cos theta. Yeah? Because this approximation relies on, that approximation relies on the continuity of the function cosine. So that relies on, oops, that's not a cos wave. It's a trig function, but it's not a cos wave. So here's my cos wave. This is theta. This is theta plus delta theta over 2. Now, if delta theta over 2 is small, then the value of the cosine at those two angles is close. But obviously, if delta theta is big, I'm just going to somewhere completely different on the cos wave. And similarly, the approximating this chord by the arc length is a good approximation if I just pick 2 points on the circle that are close. But if I pick 2 points on the circle which are far apart, let's do like 90 degrees, it's clearly much further to go round the circle than it is to cut across and do a straight line. Ooh, if theta is small, would we have a better accurate answer for theta? Yes. Right. Is there a better derivative formula for trig that gives the exact rate of change without relying on theta being small? Well, that's a very good question. But the point is that differentiation is a limit. Differentiation is a limit of the rate of change of the, because it's the gradient of the tangent. It's the limit of the change in the function divided by the change in theta when theta becomes very small. Okay, so what I've really established here is that that as theta becomes really small, that ratio between the growth of sine theta and theta tends to cos theta. So that's why there's an approximation sign here about the fraction, but there's an equality here in terms of the derivative. I suppose the exact expression for sine theta plus delta theta minus sine theta over delta theta, the exact expression is cos theta plus delta theta over 2 times 2 sine delta theta over 2. So that's the exact, sorry, 2 sine delta theta over 2 over delta theta. And then of those two parts, okay, this bit so the cos theta plus delta theta, that goes to cos theta. The other, the fraction here goes to 1. But it goes, can anyone notice what assumption I've made about the way the angles are measured that guarantees that this ratio here goes to 1 rather than some other number? And we had a long discussion about this last time. Yeah. But, you know, blink and you miss it. Here, when I found the arc length, it relied crucially on me being in it relied crucially on me being in radians. Here's a very someone said, can you get a better approximation? Have people, I know we're on a sheet on differentiation, but have people here studied integration? If so, put your put a thumbs up in. If not, just put a no in and I'll do something different. Oh, okay. Some people have done integration. Right. I'm going to do something which I think you'll find is really, really, really cool. Okay. So what I'm going to do is I'm going to try and find the area under under sort of a sine. I'm going to no. What am I going to do? I'm going to find the area under. I'm going to start with a cosine wave. Okay, so here's my cos wave. And I'm going to go to a theta. And theta is going to be positive, but much less than pi over 2. Right. I would hope that the first thing you'd agree with is that the area under the cosine wave, so which is the integral from 0 to theta of cos x dx, is less than the rectangle that is just height 1. Okay, but the rectangle which is height 1 and width theta has just got area theta. I would also hope that you'd agree with me that the area under the curve is bigger than 0. Okay. So what we can do now is we can integrate, and we know that the integral of cos theta is sine x, because we've just shown that sine x differentiates to cos x. And then when I put in my limits, I get that 0 is less than sine theta is less than theta. Okay. And this actually puts sort of mathematical flesh on the bones of when we said that sine theta is approximately equal to delta theta. Right. What I'm going to do next is I'm going to integrate again. Okay, so I'm going to integrate these functions. I'm going to note that 0 is less than sine x is less than x. And now I'm going to integrate this between 0 and theta. So between 0 and theta, I get the integral of 0, which is just going to be 0, is less than the integral between 0 and theta of sine x. is less than the integral between 0 and theta of x. Okay. And so now I get 0 is less than, right, the integral of sine theta is negative cos theta. So I get negative cos x, evaluated between naught and theta. And then this is the integral of x is half x squared. And then I evaluate that between naught and theta. So I get naught is less than negative cos theta plus 1, which is less than a half theta squared. So I now get for small theta, that cos theta is less than 1, which we knew, but is greater than 1 minus a half theta squared. Okay. Now what I can do is I can integrate again. Okay. And when I integrate 1 minus a half theta squared, that will integrate to theta minus 1/6 theta cubed is less than sine theta is less than theta. Now, what am I doing here? Well, I'm answering your question of how do you get better approximations? So if I want to approximate sine theta when theta is small, the most sort of, not the most naive, the first approximation I could get is by differentiation. And I could just say that the gradient of sine theta, the gradient of the tangent of sine theta at naught is 1. So I get this linear approximation that sine theta is approximately theta. Okay, and that's what differentiation is doing. It's giving you a linear approximation. But what I've done here, and someone in the chat says, is this a kind of binomial? Is this a binomial kind of expansion for sine x? Yes, it's exactly what it is. Okay, because what I've got here is that theta is a good approximation for sine theta, but if I was to approximate it by a cubic, I would get a better approximation. Okay, and so that cubic is not just taking into account the derivative, but it's also taking into account the way the derivative is changing. Okay, so it's clear that the sine theta graph is getting less steep, so theta is an overestimate. The minus 1/6 sine theta cubed is taking into account the fact that the gradient is changing, so you get a better approximation. And this actually becomes kind of more and more important in sort of, maths and physics, because it might be that your linear approximation is just not good enough. Now, what I'm going to do, and you probably sort of guessed what I can do next, is I can integrate 2 more times. Okay, because when I integrate sine theta once, it takes me to negative cos theta. When I integrate again, I go to cos theta. Just trust me that what I can now do is integrate 2 more times, and the theta becomes theta minus 1/6 theta cubed. That becomes my lower bound again. But when I integrate the theta minus 1/6 theta cubed, it goes to 1 minus half theta squared minus 1/24 theta fourth. And then when I integrate again, it gives me a new upper bound coming from this previous lower bound of theta minus 1/6 theta cubed plus 1/120th, which is 1/5 factorial, theta to the 5. And this process can be continued indefinitely, and this gives you better and better approximation, gives you better and better approximations to a function. Okay, and someone's recognized the name of this. The name of this process is called a Taylor approximation. Okay, a good way of visualizing this idea, and this is not just for sine and cosine, this is for any function. Let's imagine you've got the economy of a country. Okay, so let's try and not be pessimistic about Britain. Let's imagine you've got an economy and a country is growing. Let's say that you were to visit this country in a week's time. Okay, well, you'd probably say in the course of a week, the economy is not going to change very much. So you'd just say that the function a short time in the future is just going to be pretty much the same as today. But maybe if you go in a month's time or a year's time, you want to take into account the way that the function is changing. And if you just take into account the first derivative, then you would change in line with the tangent. And so your change would be f dash t delta t. But then if you want to take into account the change in the tangent, okay, so you can see here, this curve is getting steeper. You could then say, right, I'm going to factor the second derivative. I'm now going to assume the second derivative is constant. And then what that means is that the gradient is going to increase and you get this sort of quadratic term. Okay. You will probably know this from the physics. You know that there's a constant, you know the constant acceleration formula. You know that the formula for constant, for displacement, if you've just got constant acceleration, is the initial displacement. Then your initial velocity, or your velocity at time t, your velocity at time t, so ut, delta t, and then 1/2 at delta t squared. So if you take into account the changing of the derivative, you include a quadratic term. Okay, now you don't learn it in A-level physics, okay? But if you could easily write down, expressions for if you had a constant, not acceleration, but if you had a constant derivative of acceleration. And the derivative of acceleration, physicists talk about it less, but it's called jerk. So if you had a constant jerk, you would then get a third order term, and it would turn out that it would be 1/6 of the, and I won't use JT for jerk, I'm just going to call it the triple derivative delta t cubed. And so, as you can see, you're now getting better and better approximations by taking more and more derivatives. Okay, and that's, so your question of how small does theta need to be small depends on your level of accuracy. But if just taking the first derivative is not good enough, you need to take more derivatives. If you want equality, then you have to just continue this process forever, and you can get an infinite expression for sine theta. Okay. If people are happy with that, put thumbs up. If people have got any questions, put questions. And what I'll do next is I'll do some problems from your problem sheet. So if you want me to go over a problem from your problem sheet, then please just put a request into the chat. Great. So we've got thumbs up for liking that little bit of theory. And I do like doing theory with you. Someone earlier said they wanted me to do question 19, but in my sheet I've only got 18 questions. Oh, from Maths 02, not 03. Ooh, a minute, I'm going to have to look. I'm going to have to look at for maths 1202, sorry. Sorry about this. So, COMPOS main 12. So I need to recompile. Oh, where's that gone to? Ah, this looks like, no, this looks nice. Oh my God. Ha. I must have read your mind. So either that or the evil geniuses who wrote these sheets were very clever. Okay, because so this identity, here, cos theta plus cos phi, is equal to 2 cos theta plus phi, 2 cos theta minus phi. Look, okay, I could actually get this from exactly the same diagram that I had at the beginning, because I did everything with sines. But if I draw this length here is 1, and this angle is A, this is cos A. This length here is 1, this length here is cos B. So this whole horizontal distance is cos A plus cos B. But then if I just zoom out and look at the big triangle, the hypotenuse of the big triangle, as before, is 2 cos B minus A over 2. And then the base of the big triangle is then the hypotenuse multiplied by the cosine of this angle, but this angle is B plus A over 2. So that gives me a completely geometric proof of that. I'm going to give you now an algebraic proof of this, okay, which I don't like as much, but this is more of a trigonometric proof, or trig identities based proof. I could just note that cos theta, well, theta is theta plus phi plus theta minus phi over 2. But if I use my cos addition formula, I can write this as cos theta plus phi over 2, cos theta minus phi over 2, minus sine theta plus phi over 2, sine theta minus phi over 2. Cos phi, I can play exactly the same game I can write phi as theta plus phi over 2 minus theta minus phi over 2. So this time the thetas disappear, and my phi minus minus phi on the numerator becomes plus phi. And then we get a similar thing. The cos term is the same, but then the sine term changes. Sine. The sine term changes sign. That always happens. I don't know if that's, I'm sure that's got nothing to do with why the name of sine is sine. Okay. But now if we add, these terms just go away. So if we were to add, and remember that these things on the left were just complicated ways of writing theta and phi. So I could write cos theta plus cos phi is 2 lots of cos theta plus phi over 2, cos theta minus phi over 2. And as a sort of buy one, get one free deal, if I just subtract cos theta and cos phi, the cos terms go away, but the sine terms reinforce. And notice we get a minus sign. Right. I'm visualizing the scene now of sort of complaints to Vlad, yeah? So like all emailing him and saying, this webinar wasn't what we signed up for because David came on and then he just started doing trig questions. Right, question for the chat. Which of these two identities could be useful to get the derivative of cos from first principles? Do you recognize anything that might be useful for differentiation? Well, actually, it's very, very, very similar to what I did right at the beginning. Because if I say that my theta and phi, if I put as my theta plus delta theta, and my phi as cos theta, so my phi is theta, I get minus 2 sine theta plus delta theta over 2. And then I get sine of delta theta over 2. Ah, but this is familiar because sine delta theta over 2 is just a sine of a small angle. Okay, and what we know about sine of a small angle we know that to a very, 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 very good approximation, sine of a small angle is sine theta is approximately theta. And we actually know more. We know that the error is at most 1/6 theta cubed. Okay, so from this, I know that if theta is small, sine theta over theta is less than 1, but bigger than 1 minus 1/6 theta squared. Okay, so what I've got is sine theta over theta is sandwiched between the constant function 1 and this quadratic function 1 minus 1/6 theta squared. And sine theta over theta is always jammed in between those. So if theta becomes small, sine theta over theta for sure becomes close to 1. Okay, so all I need to do now is do divide by my delta theta. So I've got cos theta plus delta theta minus cos theta over delta theta is equal to sine theta plus delta theta over 2, and then sine delta theta over 2, and I'll write the multiplication by 2 as a division by delta. So to get that 2, I could divide by delta theta over 2. Now, two things I now know for sure happens. This fraction for sure goes to 1. Or I've lost my minus sign. This expression here, minus sine the theta plus delta theta over 2, well, as delta theta becomes small, that just term vanishes. So this term just becomes minus sine theta. So in the limit, as delta theta goes to 0, cos theta plus delta theta minus cos theta over delta theta just goes to minus sine theta. And what we've got here is now a proof that the derivative of cos theta is minus sine theta. And what we've actually improved, and when I asked you earlier to put a thumbs up if you sort of bought the argument, okay, what we've improved through the work that we've done is earlier, I just said that if delta theta is small, we can just look at this diagram and then say geometrically 2 sine theta delta theta over 2 is approximately equal to delta theta. So we just did I did a little bit of what's the technical term is hand waving. Whereas the extra work that we've done here allowed me not just to do hand waving, but to really have a rigorous proof for why in the limit sine theta over theta goes to 1. Okay. And so I've done a better proof of cos theta plus delta theta minus cos theta over delta theta. Okay. Now it's a too technical exercise, but I think a really good thing to go away and do now is think about what you would get if you then took these better estimates that we've got for sine delta theta and then fed them into cos theta plus delta theta minus cos theta. So that actually worked out really, really, really well as a link between the two sheets. But it also reminds me that the question that people were uncertain of was 19A. Okay, so I'm going to go back and do 19A. And again, I'm going to cover my back if you were to complain to Vlad and say that this is trigonometry rather than differentiation. Right, so we want to look at sine 3x. Well, we understand double angles, so I can write it as sine 2x plus x. Then I can just use my compound angle formula to get sine 2x cos x plus cos 2x sine x. Sine 2x, of course, is 2 cos x sine x. So it becomes 2 cos squared x sine x. Cos 2x is I'll do it this way. It's 2 cos squared x minus 1. So this gives me 4 cos squared x sine x minus sine x. But if I look at what they were trying to get me to prove, everything on the right just had signs in it. But I can rewrite the cos squared x as 1 minus sine squared x. And then if I open the brackets, I get 4 sine x minus sine x, which is 3 sine x, And then I get minus 4 sine cubed x. Okay. Let's imagine we've just proved that. Can anyone give me a super speedy way of getting an expression for cos 3x that doesn't involve all this guff that I've just done? Excellent, well done. Okay, so someone's seen the link, okay, and this is where I can sort of save my back and say, right, this really is a differentiation sheet, because if I've proved the result for sine 3x, if I differentiate on the left, I just get 3 cos 3x. If I differentiate on the right, my sine x goes to cos x. My sine cubed x differentiates to make 12 sine squared x cos x. Okay, I've just done the chain rule. Yeah, this is sine x cubed. So when I differentiate the cube. So I get 3 sine x all squared. And then I differentiate inside the brackets and get cos x. I can then divide by 3. Cos 3x is cos x minus 4 sine squared x cos x. And then I can just play exactly the same game. And then I'm done. Okay, I'll just show you one very, very, very nice thing that you can do. Okay. And I'm just going to use part C for this. Okay. Actually, I'll just do a special case. Okay. So we've got this expression. We've got cos A plus cos B is 2 cos A plus B over 2 cos A minus B over 2. What therefore is cos 5x plus cos 3x? Oh no, wait a minute. No, sorry. I'm going to do cos 4x plus cos 2x. Well, it's 2 cos 3x times cos of the difference. So 4x minus 2x is 2x, divided by 2 is cos x. So cos 4x is cos 4x is 2 cos 3x cos x minus cos 2x. But what do we know? We know that cos 3x is, what is it? 4 cos cubed x minus 3 cos x. So I can write this as 2, 4 cos cubed x minus cos x times cos x minus cos 2x, which I know is 1 minus cos squared x. So I can write this as 8 cos cubed x minus 2 cos squared x minus 1 plus cos squared x. So it's 8 cos cubed x minus cos squared x minus 1. A little bit. Oh, sorry, this needed a 3. So this is minus 6 cos squared x minus 1. Okay. What general... Oh, yes, yes, and this is 2. Sorry, this is 2 cos squared x minus 1. So this becomes plus 1. Sorry, so this becomes... This is better. Okay. Right. Question, everybody. Oh, and then I'll answer a question that's come in about degrees rather than radians. Focusing on this part here, I ended up with a formula for cos 4x. Now, don't do it, but how could I find an expression for cos 5x? And what form would that expression for cos 5x have? Well, what I could do for cos 5x is I could write cos 5x plus cos 3x is 2 cos 4x cos x. And what I could then do is use this polynomial in cosine for my cos 4x term. And that would give me something which begins 16 cos 5x. And then it would give me some lower order terms. I would then subtract my expression for cos 3x, which is a polynomial in cos. So what I end up with is a polynomial in cos x. So cos 5x is 16 cos to the 5x, and then it turns out to be something times, so some coefficient of cos cubed x, and then some coefficient of cos x, and you just get odd powers. Cos 6x, I could just play exactly the same game and do cos 6x plus cos 4x is equal to 2 cos 5x cos x. And then I multiply by 2, and I get a leading order term of 32 cos 6x. So I get cos 6x is 32 cos 6x plus stuff. So cosine can always be written as a polynomial. Cos of a multiple angle can always be written as a polynomial in cos x. And those are very heavily studied polynomials, and they were first studied by a mathematician called Chebyshev. So they're called the Chebyshev polynomials. And they crop up a lot in physics. I'm going to answer a question which I had earlier about what would happen if you use degrees. Okay, so why not degrees? Well, let's think about sine theta plus delta theta minus sine theta, which we know we can write as 2 cos theta plus delta theta over 2 times sine delta theta over 2. And now let's just, because it's simplest, let's just do the hand wavy one. So 2 sine delta theta over 2. If we just do the hand waving, it's that length. What we can equate that length to is the arc length AB. But now let's just go back and remind ourselves what we did to get the arc length. Well, look, previously I did this calculation here. Can you see? And within this calculation, I used the fact that I was measuring in radians because my complete angle was 2 pi. So my arc length AB, if I measure stupidly, so if I measure in degrees, is the angle delta theta. And as a fraction of the full circle, that's delta theta over 2 theta. And then I multiply by 2 pi. And so I get delta theta over 180. Sorry, pi delta theta over 180. And so what that turns into is I then get that sine theta plus delta theta minus sine theta over delta theta. Well, the 2 sine delta theta is approximately pi over 180. So what I get is I now get this new awkward factor, which is pi over 180. The cos theta plus delta theta over 2 goes to cos theta again. Okay, so I get this yuck factor. Okay, can anyone, that was a geometric theoretical proof. Okay, and obviously because you're still learning, that's better. Okay, how could you just get a simpler way of seeing that you get this factor? Well, if we introduce the function sine x degrees, okay, what do you need to do to an angle to convert it from radians into degrees? Okay, so x radians, okay, well, 180 degrees is pi radians. So if you take an angle in radians, and divide by pi and multiply by 180, sorry, I'm just going to get this scaling right. So x x degrees is pi over 180 times x radians. Okay. So sine x degrees in radians is sine of pi 180 times x. And now if we differentiate, we can just use the chain rule. So the sine becomes a cos, so we just get cos pi over 180 x, which is just cos degrees. But when we differentiate by the chain rule, we pick up this factor pi by 180. Okay. For those of you who were here last week, I derive the expressions for the derivative and sine and cos by going round in a circle at unit speed. And if I go round in a circle in unit speed, then cos theta over cos theta sine theta as a vector just differentiates to minus sine theta cos theta. Okay. But obviously, if instead of going round at unit speed, which does 1 radian per second, I only do 1 degree per second, then instead of taking me 2 pi seconds to go round the circle, it takes me 360 seconds to go round the circle. So I'm much slower. So if I went round the circle in degrees, the direction would still be perpendicular to my angle measured in degrees, but my speed would be a factor of pi 180. I'll just tell you a little funny fact. So my favorite computing environment of choice to do mathematics, I'm a big fan of a program called Mathematica. And obviously Mathematica, like any sensible program, would use radians for all its trig functions. And so in Mathematica, it does have a little symbol, which is this little circle. But there's a really interesting thing. And I think that this just works in all situations. So the way that Mathematica reads this symbol, okay, so this degree sign in Mathematica, if you actually look into the guts and innards of what it thinks it is, it thinks that that degree sign is just a shorthand for a number, and that number is pi over 180. So it treats this degree symbol as just the number pi over 180. So it just regards 60 degrees as being 60 times pi over 180, which is the same as pi over 3. Okay, so it doesn't regard a degree as an angle measurement. It treats it as just as a numerical conversion. Someone has asked, I should have checked the chat earlier. Somebody has asked me a very good question. How come it jumps from cos cubed to cos 5x? Notice that when I use this formula, for my addition of cosines, I want, in order to keep it as a polynomial in x, I want this term, the cos a minus b over 2, to be like a cos x. So what I do is I always choose these two numbers to be 2 apart. And then that guarantees that the expression at the end here is cos x. Yeah, so it just stays as a nice, polynomial. Okay, what you could obviously do as well is you could do something like cos 8x plus cos 2x is then 2 lots of cos 5x, and then half of the difference is cos 3x. So then you could use your polynomials cos 5x, cos 3x, and cos 2x to make cos 8x. Okay, so there's lots of ways of making the later polynomials from the early ones. So it's a kind of recursion. Okay, if you're happy now with my differentiation of sine and cos in degrees, does anyone have any final questions, quick questions you would like me to go through before we finish the webinar? Is everybody still there? Was everyone happy with the last bit? Does anyone want me to go over any of the last bit? And does anyone have any final questions? Otherwise, I will finish. Oh, Rakesh, what's your question? Oh, so there was a question, what's the final answer for cos 4x? It's here. It's 8 cos cubed x minus 8 cos squared x minus 1. Notice you could do this in a different way. You could do cos 4x is 2 times 2x. So then that would be 2 cos 2x all squared minus 1. And so it would be 2 cos squared x minus 1 all squared minus 1. And then when you square the 2 cos squared x minus 1, you get 4 cos squared x, which when you multiply it by 2 is 8 cos 4x. Then you get minus 8 cos 4x, and then you get a plus 1. Sorry, this is plus 1. So the final answer for cos 4x is 8 cos 4x plus 8 cos squared x plus 1. Okay, on problem 12, the third assignment, what is the best way to represent the tangent points on the two separate functions? Okay, let's have a look at that quickly. So I'll just need to pull up that question. This was problem 12. Find the equation of a line which is tangent to both y equals x squared plus 3x and y equals x squared minus x. So I think undoubtedly was it x squared minus 3x? Well, x squared plus 3x and x squared minus x. I think undoubtedly, in my mind, there is no question in my mind that you're best off doing this with discriminants, okay? Because you've got such a nice condition for when a line is a tangent. So we've got x squared minus, plus 3 minus mx minus c equals 0. And then you can just get a discriminant. So 3 minus m squared plus 4c is equal to 0. And then if you do the same thing here, you get x squared minus 1 plus m x minus c is equal to 0. And then you get a discriminant 1 plus m squared plus 4c equals 0. There's absolutely no doubt in my mind that then this is nicest, because now you can just equate 3 minus m is equal to 3 minus m squared is equal to 1 plus m squared. And there's two conditions. You've either got 3 minus m is equal to 1 plus m, which just gives you m is equal to 1, or you've got 3 minus m is minus 1 minus m, which doesn't work. And then once you know M, you can figure out C. C is -1. Okay. Is that too much of a cop-out? Ah, sorry, I should have checked the crest. Okay, but what method, what's the best method to do it with calculus? I mean, to be honest, the best method to do it with calculus is just the following. Okay. If you take a general quadratic, y equals x squared plus bx plus c is equal to 0, and then consider the tangent at A. Yeah, Lottie, just 5 minutes. At A, okay, my daughter's hungry, so I'll do this very quickly. So at A, you just say that the derivative is 2a plus b, and then you fit the point. So the general tangent is y minus a squared plus ba plus c is equal to 2a plus b x minus a. Okay. And so then what you've got is you've got a straight line, which is 2a plus b x plus a squared plus ab plus c minus 2a squared, I'm just opening the brackets here, minus 2a squared minus ab minus ab. So that is, the ab's cancel, so you get y equals 2a plus bx plus c minus a squared. But now what you can do is you can now find an algebraic relationship between M and C, okay, in terms of the coefficients of the quadratic. Yeah, you've just got that you've just got the M squared. Well, what oops. Sorry, I've just lost my window. Okay, so what you've got here is that if you take the gradient of your line and subtract b, you get 2a. And if you take your if you just take your the c in your line and you subtract the c here, then you get minus a squared. So what you've got here is m minus b squared. This is for any tangent, is 4a squared, and that is the same as 4c wait a minute, is equal to 4c minus c. You get m minus b squared plus c is equal to 4c. But if you then apply that to the two lines, you will get equations that link the gradient of the line M to its y-intercept C. Okay, but surprise, surprise, the algebraic conditions that you'll get in each case is just exactly the same as the algebraic condition that you got from the discriminant. So using calculus to find the gradient at a general point will give you an algebraic condition linking the gradient and intercept of a line, but it'll just give you the same algebraic condition that you could have got more conveniently from using the discriminant. Okay, I'm not going to give, people have been brilliant at asking questions. My daughter just came into the room a minute ago saying she was hungry, so I'm not going to give you the option to write, to ask any more questions. So we'll finish there. I hope everybody enjoyed the webinar. Apologies about the technical things at the start, but once it got going, I hope it was good. Cool. I'm getting some thanks in the chat. Brilliant. Great. Enjoy the rest of your evening. I'm just going to go and cook dinner for my daughter. Okay. Bye-bye, everybody.